Hi, in this video we're going to look at the reaction of an acid and a base where neither of them are water. We'll choose as our acid the acetic acid, and we'll choose as our base ammonia. And they will react to make their conjugate acids and bases. The conjugate base of acetic acid is CH3CO2 minus, and the conjugate acid of NH3 is NH4 plus. So we're using Bronsted-Lowry theory. This is the acid, this is the base. The acid turns into the conjugate base and the conjugate acid. And we know quite a bit about these acids, about these materials. We'll look at their Kas. So the Ka of CH3CO2H is 1.8 times 10 to the minus 5 molar. It's the pKa of CH3CO2H is 4.74. And we can actually rewrite the Ka using that number. It's 10 to the minus 4.74. And we can look similarly at the Ka of the conjugate acid, NH4 plus, which is 5.6 times 10 to the minus 9 molar, with a pKa NH4 plus of 8.24. And we can rewrite the Ka of NH4 plus with that 8.24, 10 to the minus 8.24. And what we see is that the acetic acid is 3.5 orders of magnitude stronger than the ammonium acid. So this is the stronger acid. And this is the conjugate is the weaker acid. And we know if the acid is stronger, its conjugate base is weaker. So this is going to be the weaker base and the stronger base. And we see then that we think this reaction will occur because both the acid and base are stronger than the conjugate acid and base. But we can also use these numbers that we have here to figure out exactly how much this reaction occurs. And we're going to call this reaction number 1. Just we'll have a name for it. And we're going to look at its Ka. The K for reaction 1. And that's going to be equal to the product concentrations, CH3CO2 minus, times the other product concentration, which is NH4 plus, and we're going to divide that by the reactant concentrations, which are CH3CO2H, and the other reactant is NH3. And what we're going to do is we're going to break this apart into CH3CO2 minus, and I'm going to add to that an H3O plus, into the numerator here, and if I add the H3O plus to the numerator, I must now also add it to the denominator. So I'll do that here. So this is good because there's an H3O plus in the numerator that's added and one in the denominator that's added, so it's still equal to this expression right here. And this is good because that expression in blue that we have is Ka of acetic acid. And that expression we have in aqua right next to it is related to the Ka of NH4 plus, except for that the NH4 plus here is in the numerator, it should be in the denominator. The NH3 and the H3O plus should be in the numerator and the denominator. It's switched. It, in fact, is Ka of NH4 plus inverted to the -1 power. And we can now plug in their values. The Ka for CH3CO is 10 to the -4.74. And now we have to divide that, since we're taking the inverse of the Ka of ammonium, which is 10 to the -8.24. And if we do that math, we see that this is equal to 3.50. So this reaction does indeed occur. It occurs to a K of between 3.5 orders of magnitude, so between 1,000 and 10,000. So it really occurs a lot, just as we predicted, because it is a stronger acid reacting with a stronger base to make a weaker acid and weaker base. And we'll practice this in tomorrow's lab.